Hello students, in this video we'll prove three relatively simple propositions using the Peano axioms. So the first proposition we're going to prove is the following. Proposition is that S, if n is not equal to m, then S of n, the successor of n, is not equal to the successor of m for n in m in n. And so how do we prove this proposition? Well, recall, proof, axiom number 3, Peano axiom number 3, stated that if Sn was equal to Sm, then this implies that n is equal to m. And so our statement is just a contrapositive of this. So our statement is a contrapositive. And so our result is true. 1, 2, 3, 4. There we go. So that's the first statement. So in other words, if two natural numbers are not the same, then their successors are not the same. That's going to come up a lot in our sort of formal construction of the natural numbers. The second proposition we'll prove is that for any natural number n is not equal to its successor. And here's where we're going to use mathematical induction, or the fifth Peano axiom. So I'm going to consider a set M, which is the set of all n in n, such that n is not equal to its successor. And now what can we say about this set M? Well, one thing we know is that the second Peano axiom, axiom number 2, or it might have been axiom number 3 maybe, axiom 2 or 3, we don't remember exactly what it is. This might have been 3 or 4, so the axioms might be a little bit off. So I think this is probably axiom number, that's probably axiom number 4 from our previous video. So this is axiom number 3, says that 1 is not the successor of any number, and so that implies that 1 is not equal to the successor of 1. So in other words, what do we know? We know that 1 is in the set M. So this tells me that 1 is in the set M. Now, if n is in the set M, then this implies that n is not equal to the successor of n. And now I can use this previous proposition. So by our previous proposition, I know that if m and n are not equal to each other, then their successors are not equal. So s of n is not equal to s of n. And this statement exactly shows that s of n is in m. So this implies that s of n is in m. So what do we have? We have that n in m implies that Sn is in m. So I have 1 is in m in this statement. So by axiom 5, this implies that m is equal to the entire set of natural numbers. Excellent. So in other words, this statement holds for any natural number. Now the last statement we'll prove is this. The final proposition, is that if n is not equal to 1, then there is a unique value m in n such that n is the successor of m. And so we're going to prove this statement by induction. So in other words, every natural number comes from the successor of something else. We can think of this m as the predecessor in some sense. So how do we prove this? Here's our proof. Our proof is we're going to let m be the set 1. So we're going to force 1 to be in the set. And the set of n in n such that the statement is true. The prop is true. Okay, so clearly 1 is in this set M by definition. And then if I give you an n in m, n in m implies that n is equal to s of m for some value of m. That's what that statement means. The proposition is true. And then I can take the successor of both these things. This will imply that the successor of n is equal to the successor of the successor of m. And so the value m in this case will just be the successor of m. So I've shown that if n is in m, then Sn is in m. So Sn is in m. And then by axiom 5 implies that m is equal to the set of natural numbers. In other words, if n is not equal to 1, then that number n is the successor of some other natural number, m. Thank you very much.